In this lecture, we will see the schematic diagram of a 2-input XNOR gate. Then we will draw the twisted schematic from the normal schematic and then the layout. So this is a 2-input XNOR gate. Okay. So let's see the symbol of a 2-input XNOR gate. We'll see the symbol first, then we'll see the function, and then we'll see the truth table. Okay, the symbol of a 2-input XNOR gate is this is a XOR gate, then a bubble. This is the symbol of a 2-input XNOR gate. This is the output Y. So Y is equal to A XNOR B. This is the symbol of XNOR. The function is Y is equal to A bar B bar plus AB. That is A XOR B whole bar. The truth table of a 2-input XNOR gate is, this is A, this is B, this is Y. Let's make a proper straight line. If input is 0, if both inputs are 0, then the output is 1. With 0, 1, then 0, then 1, 0, then 0, 1, 1, then 1. So you can see the output of the truth table is just reverse the output of the XOR gate. So that's the reason why it's written A XOR B whole bar. So if you want to explain the truth table, then you can write if both the inputs are equal, that is A is equal to B, then Y is 1. If A is not equal to B, then Y is 0. Or in other terms, you can say if the number of ones is odd, then Y is equal to 0, else it is 1. Okay, so now let's see the schematic diagram of a 2-input XNOR gate. So Y y is equal to a bar b bar plus a b. So you can see here this is a bar and b bar. So there are two inverters. So the number of gates needed in order to implement this function. If you try to draw the schematic from the function, this is if you try to draw the schematic keeping in mind the function. Okay, if you try to draw the schematic keeping in mind the function, then the number of gates needed, NOT gate, will be 2 for a bar and b bar. Then you need AND gate for a bar b bar and for ab, that is again 2. Then the number of OR gates needed, that is 1, that is for a bar b bar plus ab. So now if you try to implement this at a gate level diagram, then you need two inverters. First, if there are two inverters, this is for A, this is B, this is A bar and this is B bar. So first will be A bar B bar, this is A bar, this is B bar. The next this is A, this is B. Okay, so this is A bar dot B bar and this is A dot B. This is the OR gate. This is the final output Y. So you can see two inverters, two AND gate, a NOT and a OR gate. Now if you expand this in the schematic, this is the gate level. So now let's see at the transistor level. For two inverters, okay, let's see the previous page. For implementing two NOT gates, we need two PMOS and two NMOS. For implementing two AND gates, we need 4 PMOS and 4 NMOS. For implementing one OR gate, we need 2 PMOS and 2 NMOS. So if we follow this, then the total number of PMOS and NMOS needed will be 8 PMOS and 8 NMOS. Keep this in mind. We should always try to minimize this, the number of PMOS and NMOS. So we'll see that later on. How will you minimize that? So first, draw the schematic by using this function. So first, the inverter. For a inverter, you need, so this is the inverter. First inverter, now this is the NMOS. Okay. Suppose this is the input A, then you'll obtain the output as A bar. Now inverter 2, this has input B and output will be B bar. So they have a common ground and a common VDD. So after drawing the inverter, we need two and two and one OR. For designing a AND gate, we know that the NMOS will be in series and the PMOS will be in parallel. So this is 1, 2 PMOS, they are in parallel and the NMOS is in series. Sorry, I made it wrong. The two PMOS will be in parallel. So they are in parallel and the NMOS is in series. So this is a AND gate. In the OR gate, it will have just the previous one. So suppose this is A bar, this is B bar, this is again A bar, this is B bar. That you'll obtain from here. This is B bar, this will be same as this, then this is A bar, so it will connect from here. This is again connected to VDD and these are connected to the ground. Okay, so now we need similarly another AND gate. Okay, here it's A, B, this is A and this is B. Then we need a OR gate where the PMOS are in series and the NMOS are in parallel. Okay, these have the input A bar, B bar and AB. Similarly here, this is the final output Y that gives the output A XNOR B. So now you can see it's too complicated to draw the twisted schematic of this and then the layout. So what we will do, we'll draw the layout from the schematic by using the transmission gate. So let's see in what way you can reduce this number of PMOS and NMOS. This can be done by drawing the schematic keeping in mind the truth table of XNOR gate. So you can write it as schematic from truth table. Okay, so now how will you draw the schematic from the truth table? Truth table is 0 0 1 0 1 0 1 0 0 1 1 1. So let us draw two transmission gates first. This is the transmission gate 1 and then we have another transmission gate. This is the transmission gate 2. Okay, this is input 1, input 2, combine, and you'll get output Y. So we give the input as B bar. This is your A, this is A, this is A bar. So this is the twisted schematic, sorry, not the twisted, the normal schematic using the truth table, that is using transmission gate. So this is the schematic using the transmission gate. Now if you want to verify, we can verify the truth table, but that will do later on. First let's draw the twisted schematic. Now before drawing the twisted schematic, you have to draw two more circuit here, because you have to get the inverters also. So what we will do, we'll add two more inverters over here. This is inverter 1, this is inverter 2. Okay, this is input A, this is the output A bar. Similarly, we need one more inverter. Okay, now this is connected to VDD and this is connected to ground. From here you have input B and the output is B bar. So from here, this is B, this is B bar. Sorry, this is B and this is B bar. So B bar is connected over here and B is connected from here. Okay, B is connected, then A is connected here and A bar is connected here. So A bar is connected from here and A is connected here. Okay, so this is the schematic from the normal schematic. This is P1, P2, P3, P4, N1, N2, then N3 and N4. So you can see there are 4 PMOS and 4 NMOS. So we all know the terminals. This is source, this is drain, this is drain, source. You know, these are drain, these are source, drain, and source drain. So next you have to draw the twisted schematic from this normal schematic. So now let's see the twisted schematic diagram of a XNOR gate. So as we all know how the twisted schematic diagram of XNOR gate can be, that is, we'll have 4 PMOS twisted, 4 NMOS twisted. So draw that first. This is PMOS 1. This is PMOS 2. This is PMOS 3 and this is PMOS 4. Similarly, we'll have the NMOS. This is NMOS 1. This is NMOS 2. NMOS 3. And this is NMOS 4. This is P1, P2, P3, P4, N1, N2, N3 and N4. So this is not required actually, the source and drain, because the source and drain is same for all. Source and drain, but here just for our convenience we have taken it as drain and source. Here again source drain, source drain, source drain, drain and source. In Exor case we had taken just the reverse one. If you want you can do that also. So now these two are the transmission gate, these two are the inverters, or you can take these two are the inverters and these two are the transmission gate. So if I say these two are the inverters, then the sources of the inverters are connected to VDD. Of the sources of the PMOS, they are connected to VDD, and the source of the NMOS are connected to ground. This is connected to ground. Drain and drain are shorted, gate and gate are shorted. This is gate to gate, this is drain to drain. This is input A, this is A bar, this is B, this is B bar. So now these are our transmission gates, so these sources are shorted, the drains and the sources. So you know that the drains of the transmission gate, they are connected to each other and that gives the output Y. These are the inputs, so we'll see what inputs are given here. So this is A. A is given as the input to this. Okay, so you have to connect the gates also. This is connected. Okay, gates are interconnected. The input A is given to this gate, so we'll connect from here to this one. Okay, this is A. Then A bar is connected to the other end, So this is A bar. A bar is connected here. This is A. Then B and B bar. B is connected to this source and B bar is connected to this source. This is the reason why we have taken source drain, then here drain and source. So B bar is connected to this input and B is connected to this input. So I'll take from here. This is B and this is B bar input given to both the source. This is the obtained output Y, and this is a twisted schematic of a XNOR gate, and we'll draw the layout from this twisted schematic. So now let's see the layout from the twisted schematic diagram. Twisted schematic. So first we have 4 PMOS. So I'll take a common anvil. So we'll draw from here. This is anvil. Then we need diffusion. P diffusions, we need 4 P diffusion. This is diffusion 1. This is P diffusion 2. You have P diffusion 3. This is the P diffusion 4. Okay. Then the N diffusion layer. First make the layout in your rough note so as to understand why this gap is given. So now this is the N diffusion layer. And diffusion layer. So now these two are the inverters, these two are the transmission gate. So design the inverter first. I have to draw the gate of the inverter. This is also the gate of the inverter. Then this is input A and B. If you see the transmission gate, then the gates are oppositely connected. So then from here to here, Okay, now the transmission gate are oppositely connected. Actually, we cannot connect from here directly because these two will again overlap, so we have to connect from here. And this is the poly. Okay, now complete this inverter. The sources connected to VDD, source connected to VDD, then the source of the NMOS is connected to ground. Then in the transmission gate, the two sources are connected and the two drains are connected. Here two drains and two sources. This is metal 1. Okay, now after this is to inverter. Okay, in the inverters the drains are not connected, so you have to connect the drains. Okay, so these are the two outputs, that is A bar and B bar. So we know that this B bar is connected to this input, so this can be done directly from here. So this give the input B bar to the first transmission gate. This is the output, and we know that the output of the transmission gate, they are shorted in order to give one output Y. Okay, so B bar is connected, then B is connected over here. So B is a poly layer. So poly layer is connected with this. So try to get from here. And then connect to this. Think we could have connected this output over here so as to bring convenience, but it's okay. So here there is a overlapping between poly and metal, so you need to place a poly contact. So you need to place a poly contact. So this is a poly contact. Then we have to connect the A. A is connected to this gate, so we can connect from here directly. This A is connected to this gate. Okay, and then A bar is connected to the other gate. So okay, so this can be connected from here to here. Okay, we'll do one thing. We'll draw from the poly layer. Whereas this poly layer is connected to this A bar. So metal, get metal from this. So there is a overlapping between metal and poly. So you need a poly contact over here. This is again a poly contact. Okay. So all input output labeling is done. Now you have to place the contacts. So this is the P diffusion contact, PDC contact. This is the P diffusion contact, P diffusion. So all these are the P diffusion. Since there are 4 sources and drains, we need 8 P diffusion contacts. This is the N diffusion contact. This is 1, 5, this is 6, this is 7, and this is 8. After placing diffusion contacts, you have to place the substrate contacts. So this is N substrate contact. Then this is P substrate contact. So this is the layout of a twisted schematic. The layout of a XNOR gate that is drawn from the twisted schematic diagram. So you can see the next lecture in order to see the layout in Magic. Now let's see the layout from the normal schematic diagram. Layout from normal schematic. In order to draw the layout from the normal schematic diagram, this area will not be sufficient. So we can do one thing. First draw the inverters. This is inverter 1. So for inverter 1, you have to draw the anvil. Then inverter 2, the second anvil. Then the P diffusion layer. This is the P diffusion layer for PMOS 1. This is the P diffusion layer for PMOS 2. Then the N diffusion layer. Okay. Now, so have to draw the gate first. Okay, this is suppose input A and this is input B. Okay, these are the sources, these are the drains, drain and sources. So the sources, this is connected to VDD and these are connected to ground. Then these drains form the output. This is A bar and this is B bar. Then we have the two transmission gates. So the layout of the two transmission gates can be done as this is NMOS 1. Sorry, that is NVEL 1. This is NVEL 2. Similarly, we need P diffusion 1, P diffusion 2. So this is NVEL, P diff. Then this NDiff. So this is one transmission gate, this is the second transmission gate. The gate of this NMOS is connected with the gate of this PMOS. So to make a connection here, then this is connected with this. So we can do one thing, we can take one hole from here, or okay, we'll draw this gate later on. First see, this A is connected to this two gate, then A bar is connected over here. So since A bar is connected to this, then B is connected to the source and B bar is connected to this source. So before drawing that, form the inputs and outputs. This is input and this is output, and this is the input and this is the output. So this B bar is connected to this directly, then B is connected to here. So take from here, so there's overlapping between this. So you have to place a metal contact over here. So here there is a poly contact. So B is connected, B bar is connected. Now this A will be connected and A bar is connected to this. A is connected to this. So make a connection from, okay, keep in this metal from here, then keep extending. This metal will be connected there. This metal will be connected to this poly. So this poly is connected with this metal. So we need a poly contact over here. This is again a poly contact. Then A is connected to both this and this. So one thing can be done. Connect this from outside. And from here it can be connected to this. Then this will be to this. Now the only thing left will be the connection between this two output of the transmission gate. So you can make it connected directly from here. This and this is output Y. Now we have to place the contacts. This is P diffusion contact. This is N diffusion contact. This is again P diffusion contact. This is N diffusion contact. P diffusion contact, N diffusion contact. P diffusion contact. And this is PDC. This is NDC contact. After that you have to place the substrate contacts, the N substrate contact. Similarly here the P substrate contact. So this is the layout from the normal schematic diagram. From normal schematic. Now let's see the explanation for the truth table. Of the truth table of the 2-input XNOR gate. Truth table. So at first let us draw the schematic and the first condition, that is when A is equal to 0 and B is equal to 0. In this case the A acts as the control signal and B is the input. So here this is transmission gate 1. This is transmission gate 2. This is B, and this is B bar. This is A, and this is A bar. A bar. Okay. Now these two are connected. This is the output Y. So if A is 0, then this is 0. This A will be 0 and this A bar will be 1. So this A is 0 and A bar is equal to 1. A is equal to 0. B 0. B bar is equal to 1. So if you see this condition, if okay, here control signal is A. So if A is 0, then this is suppose P1 N1, this is P2 and this is N2. So P1 will be on. Since we know if input is 1, then NMOS will turn on and PMOS will turn off. This will turn on. And when it's 0, then PMOS will turn on and NMOS will turn off. Okay. So here P1 will turn on and here A bar is 1. So N1 will also turn on. Here P2 is 1. So P2 will turn off. And here N2 at N2 0 is applied. So N2 will turn off. So here what will happen? The transmission gate 1, this is TG1, this is TG2. TG1 will turn on while TG2 will turn off. So here TG1 is active and TG2 is off. So when TG1 is active, then the input B bar will be available at the output Y. So Y is equal to B bar, that is equal to B0, then B bar is 1. So if A is equal to 0, B is equal to 0, then in the XNOR gate, the output Y is equal to 1. So here the first condition is verified. Now let's see the second condition. The second condition is A is equal to 0 and A is equal to 0, B is equal to 1. You have to keep in mind A is the control signal and B is the input. So once again draw the transmission gate. So this is the PMOS, this is the NMOS. PMOS, this is the NMOS. This is the input. This input is B bar. Sorry, this input is, yes, this is B bar, and this input is B. Similarly, this is A bar, and this is A. Here is the output Y. So now this is P1, N1, P2, and this is N2. So if A is equal to 0, in this case what will happen? If A is 0, then A bar is 1, A is 0. Here B bar will be 0 since B is equal to 1. So if A is 0, then P1 is activated. So P1 will turn on. If A is 1, then N1 will turn on. A bar 1 then. So P2 will turn off, and N2 will also turn off in this case. So what will happen? The transmission gate 1 is again active, while the transmission gate 2 is off. So if this is active, then again this input, the input B bar is available at the output Y. So Y is equal to B bar, which is equal to 0, since B here is 1. So B bar is 0. So here when A is equal to 0, B is equal to 1, then the output Y is equal to 0. The second condition is also verified. Now let's see the third condition. The third condition is if A is equal to 1, B is equal to 0. This is again the control, and this is the input. So here this is the PMOS 1, this is NMOS 1. This is A, this is A bar, this is A, this is B bar, this is B, this is output Y. So this is P1, N1, P2, N2. When A is 1, then A bar is 0, A is 1, here B bar is 1, B is 0. So if A is equal to 1, if A is 1, then P1 will be deactivated. It's off. Here A bar is 0, so N1 is off. Since A bar is 0, P2 will turn on and N2 will turn on. So the transmission gate 1 is now active. Sorry, the transmission gate 2 is now active since these two transistors are on, and transmission gate 1 is off. So this B will be available at the output. So Y is equal to B. So here B is 0. So if A is equal to 1, B is equal to 0, then the output Y is equal to 0. This is verified. Now let's see the fourth condition. That is if both the inputs are 1. So if both the inputs are 1, then this is transmission gate 1. This is the transmission gate 2. This is A, this is A bar, this is again A, this is B bar, B. So now this is now the output Y. So here if A is 1, then A bar equals to 0, this is 1. If B is 1, then B bar is equal to 0. This is P1, N1, this is P2, N2. So if A is equal to 1, since this is the control signal and this is the input. If A is 1, then P1 will be deactivated or it is off. Here also N1 will be off. P2 will be on and N2 will be on. From this you can see P2 is on and here N2 is on. So transmission gate 2 is now active while transmission gate 1 is off. So this input B will travel again at the output. So Y is equal to B. Here B is 1. So when A is equal to 1, B is equal to 1, then the output of a XNOR gate is 1. So this is verified.